In this example problem, we will calculate the shear capacity of the section shown using the ACI 318-14 simplified, ACI 318-14 detailed, ACI 318-19, and AASHTO LRFD general procedures. This is a simply supported beam that was tested at the University of Texas at Austin with the simple supports at the top here and a distributed load applied using an airbag along the bottom of the section. So this beam was tested to failure, and the failure load was 13.3 kips per foot. So we're going to compare our estimated strength with the actual failure strength in this example. This section is a doubly reinforced section with 5 number 11 bars as our compression steel, 5 number 11 bars as our tension steel. We have a concrete strength of 4,000 psi. The modulus shown 3,840 ksi. Our yield strength of the steel, which is a measured yield strength of 69 ksi, and our maximum aggregate size is 1 inch. Since this beam doesn't have shear reinforcement, we will need the maximum aggregate size, and we'll also need the distance between our crack control reinforcement. So we don't have any skin reinforcement in this section, so the crack control reinforcement is just the distance between our compression and tension steel, which here is 17.6 inches. The first thing that we need to do is we need to find our shear and moment diagrams for our simply supported beam with the distributed load. And we need to do this so that we can find the shear and moment at our critical section. For both AASHTO and ACI, for non-pre-stressed member, the critical section is going to be a distance d away from the face of the support. Here we don't have any support information, so we're just going to assume that the face of the support is the end, or is the center line of our support. So a distance d away from the face of the support will give us our critical and or critical shear and critical moment. We can find our maximum shear, which would be 120 kips, and our critical shear here. We have a linear slope equal to our distributed load, so we can find our shear at critical equal to 96.4. We can also find our max moment and our moment at the critical section. So our max moment at midspan and our moment at the critical section of 2300 kips. In both ACI and AASHTO procedures, when we're using our shear demand, we're going to use the shear demand at the section where we're calculating our shear strength. So we're going to find our shear strength at our critical section. So we're going to use the critical shear and critical moments in our shear strength expressions. The other thing we can do is we can calculate our shear span to depth ratio. So the shear span for a distributed load is just the ratio of our maximum moment to our maximum shear. So you can see here our max moment we found to be 6,464 kip inches, and our maximum shear was 120 kips. So our shear span is just 54 inches. Our shear span to depth ratio is 54 divided by 21.3, which will give us 2.54. We can see that this is greater than 2, so we can use our normal sectional shear approaches. If we had a shear span to depth ratio less than 2, then we need to consider this as a deep beam member, and we can use the strut and tie method in that case. We're now ready to calculate our shear capacity using our different methods, and we'll start with the simplest. So using the ACI simplified shear procedure, we'll get our VC is equal to 2 times lambda, which is 1.0 because we're using normal weight concrete, times the square root of 4,000 psi, times our BW, which is in this case 36 inches, and our D is 21.3 inches. And I'm going to take this times 1 kip per 1,000 pounds. to convert our units to kips, and we'll get 97.0 kips. We can then see we don't have any transverse steel, so our VS is going to be equal to 0. So our AV is equal to 0. So we have no transverse steel, so we have no VS component. Then our total shear resistance, our VN, is just equal to our 97.0 plus 0 equals 97.0 kips for our simplified shear method. We'll next find our shear capacity using the ACI 31814 detailed shear procedure. For ACI 31814, we will need our rho W, and this rho W is the area of our steel, which in this case, area of our tension steel, which in this case is our 5 number 11 bars, so 1.56 square inches, divided by our BW, which is 36 inches, times our D here, which is 21.3 inches, which gives us a value of 0.0102. We also need the ratio here, VU dP divided by MU, and this is at the critical section, and we'll find this to be our VU 96.4 kips, our dP 21.3 inches, divided by our M sub U of 2,300 kip inches. So this will give us a value here of 0.893. So now we can plug these values into our different VC equations. First, our VC sub A is 1.9 times a lambda of 1.0 because we have normal weight concrete times square root of 4,000 psi plus 2,500 times our 0.102 times 0.893, and then all this times 36 inches, VW times 21.3 inches, and then divided by 1,000 pounds per kip. So this will give us a VC of 109.6 kips. Next, we can plug our values into our VC B equation here. So we'll have 1.9 times 1.0 times the square root of 4,000 psi plus 2,500 times 0.0102, and then this times our 36 inches times 21.3 divided by 1,000 pounds per kip, which will give us a value here of 111.7. kips. And then finally, our VCC equation is 3.5 times 1.0 for normal weight concrete times the square root of 4,000 psi times 36 times 21.3 divided by 1,000 pounds per kip, which will give us a VCC here of 169.7 kips. So we can see the smallest of these is our 109.6, so that's the one that controls. So again, we have no shear reinforcement, so our VS component's equal to 0. So our VN then is equal to 109.6 kips. Next, we'll find our shear capacity using the ACI 31819 method. We'll find our shear capacity using the equations in the table shown in the top right. We don't have minimum shear reinforcement, so we're going to use this equation here shown in C. So in this equation, we have to find our lightweight concrete modifier, which is still 1.0 for normal weight concrete. And we also need our lambda S, which is our size effect factor. So our size effect factor is going to be the square root of 2 divided by 1 plus our D, 21.3 divided by 10, which will give us a lambda S equal to 0.8. And this needs to be less than or equal to 1. So in our case it is, so we'll use a lambda S equal to 0.8. So our VC then is going to be equal to 8 times 0.8 times 1.0, our lightweight concrete factor, times our rho W, which is the same as we found previously, equal to 0.0102 to the 1/3 power times the square root of 4,000 psi, and then plus this second term, but we don't have any axial load, so this term will be equal to 0. So when we close our parentheses, take BW 36, D 21.3 divided by 1,000 pounds per kip, which will give us a VC here equal to 67.3 kips. Again, we have no shear reinforcement, so 0 kips for our steel, so our VN is equal to 67.3 kips. We're next going to use the AASHTO LRFD general procedure. So normally when we're doing a shear design, we'll first do the flexural design. So that means that we'll have our flexural strength already. So AASHTO uses the flexural strength in the determination of what's called an effective shear depth. So our effective shear depth is D sub V, and it's equal to our nominal moment capacity M sub N divided by ASFY plus APS FPS, so non-pre-stressed steel plus pre-stressed steel component. We don't have any pre-stressed steel component, so all we have is our non-pre-stressed steel. So we have 5 number 11 bars with a yield strength of 69 KSI. Our MN, we'll say that we found before for this section, is equal to 10,274 kip inches. So we can find our DV equal to 19.1 inches. AASHTO also tells us that this DV doesn't need to be less than the greater of 0.9 D sub E and 0.72 H. So for us, 0.9 D sub E is 19.2 inches, and 0.72 H is 17.3 inches. So the max of these is 19.2, so that means that our D sub V doesn't need to be less than that value. So we'll use a D sub V equal to 19.2 moving forward. Next, we need to find our crack spacing parameter, which is S sub XE. We need to find this because we do not have minimum transverse steel. If we had minimum transverse steel, then we wouldn't need to find this parameter. So we can plug in our values that we found on the first slide, and we'll find that our SX here is equal to 17.6 times 1.38 divided by 1 inch plus 0.63, which will give us an S sub XE equal to 14.9 inches. The next thing that we need to do is we need to find our tensile strain. So this is the strain in the concrete at the location of the centroid of the tensile reinforcement, so epsilon S. And we use this value to tell us how effective the concrete is going to be at resisting shear, and also the crack angle theta. So for us, our epsilon S is going to be equal to the absolute value of 2,300 kip inches. So this is our moment at the location that we're interested in, that where we're calculating our shear, our critical section, and divided by our dV, which is 19.2 inches. We don't have any N sub U component for this problem, we don't have any pre-stress component either, and we also don't have any pre-stressing force. So we just need to add in here the absolute value of 96.4 kips. We divide this by our denominator, which we again don't have any pre-stressing component, so we only have our 29,000 KSI times our 5 number 11 bars. And we'll find our epsilon S is going to be equal to 0.000956. Note that it's positive, so we have a tensile strain here. If it was negative, we would have a compression strain, and we would also need to include the stiffness or restraint provided by the concrete. So just if your epsilon S that you find here is less than 0, then you need to change your denominator to include the concrete stiffness. So E sub C times A sub CT. But for us, it's greater than 0, so we're okay here. All right, the next thing that we can do is we can find our concrete effectiveness factor. So for us, we don't have our minimum transverse steel, so we have this second component that we need to include. So we'll have 4.8 divided by 1 plus 750 times epsilon S 0.000956. Times 51 divided by 39 plus our S sub XE, which we found to be 14.9. And we'll get our beta here to be equal to 2.65. And we're going to use this beta on the following slide to find our concrete shear component. We can also use our strain at the level of our tension steel to find the angle of our compression, or the crack angle. So this will be 29 plus 3,500 times our strain that we found on the previous slide, 0.000956. So we'll find our angle here to be 32.3 degrees. And we would use this angle if we had a steel component. So if we had some steel, we would use this angle to help us determine how much steel is crossing our cracks. So how much steel contributes to our shear strength. Since we don't need to use it. But we can use our beta to find our V sub C. So our V sub C here is going to be 0.0316 times our beta, which we found on the previous slide, 2.65, times the square root of f prime c. In AASHTO, all of our units are KSI. So just make sure that when you're using AASHTO under the square root, we use KSI. Where in ACI, we're using PSI. So just note that difference because that'll give you much different answers. So then times our 36 inches, and then times 19.2 inches, our shear depth. And this will give us a V sub C equal to 115.8 kips. We don't have any steel, and we don't have any vertical pre-stressing component, so our V sub N is just equal to our V sub C, which is 115.8 kips. So this is our V sub N value using AASHTO. This specimen failed at a shear demand of about 120 kips. So we can compare the experimental capacity of 120 kips with the calculated capacity. And you can note the failure crack. So in this specimen, because we did not have any shear reinforcement crossing the crack, as soon as this crack developed, the specimen failed. So if you have shear reinforcement there, after the shear crack develops, you'll get additional shear strength, but in this case, it failed immediately after cracking. So you can see the AASHTO detail procedure gave us our closest estimated strength, and ACI 318.19 gave us our most conservative strength estimate. You can see the simplified procedure from ACI 318.14 and the detailed procedure from ACI 318.14. Both were conservative in this case and were somewhat accurate in estimating the strength. Note though that ACI 318.14 generally becomes unconservative for larger specimens with no shear reinforcement. So there was a test at the University of Toronto where they found a strength of only about 0.7 times the square root of f prime c, where you can remember with the simplified procedure we had 2 times the square root of f prime c. So in that test with the 4-meter deep beam, they had unconservative results. And you can look at this paper by Collins et al. To see more details on that testing. So that concludes this example problem.